Okay, so the next result is Newton's approximation. And the setup of this result is the same that we see while defining differentiability. That is, we have a subset of the set of real numbers x, and x naught is a point in x which is also a limit point of x. And we have a function f with x as its domain and of course its real value. And capital L is a real number. Then we have these two statements which are logically equivalent. That means if any one of them is true, then so is the other. Now let's see the statement. The first statement is that our function f is differentiable at that point x naught on x of course, because x is the domain of f, with L as its derivative at that point. And the second statement is an inequality. It states that for every positive real number epsilon, there exists a positive real number delta such that if we choose any point x from our domain, that is delta close to x naught. That is, the distance between x and x naught is at most delta. Then we have this inequality. Now let's also see what the inequality says. It says that the distance between f of x, the function value at that point x, and f of x naught plus derivative L times x minus x naught. This distance is at most epsilon times the distance between x and x naught. And this is an approximation. Whenever you have an inequality, it's always an approximation. And this is called Newton's approximation, which means that if f is differentiable at x naught with L as its derivative, then the function value at x is approximately equal to this. Whenever you are choosing x in a neighborhood of x naught, and of course you also have to choose x from the domain because otherwise fx will lose meaning. Even more loosely speaking, it means that near x naught, choosing a neighborhood of x naught means being close to x naught. Either you are on this side of x naught or on that side of x naught. When you are very close to x naught, when you are sufficiently close to x naught, fx value is approximately equal to this expression. Now note that in this expression, actually the variable is x. All the other parts are constant. One of those parts, of course, is the value of the function at x naught itself, and the other part involves that derivative. So the derivative allows you to have such an approximation. Note one more thing, that if you are concentrating on only this part within square brackets, it's a linear function in x, because here the only variable is x and that's it. From x you are subtracting x naught, then multiplying by a constant L, and then also adding a constant f of x naught. So it's a linear function of x. That's how if a function is differentiable at x naught, very near x naught, there is a linear approximation. That means the function near that point is almost like this linear function. And that almost like, of course, is a vague term, but precisely you have this inequality. And this approximation, of course, is named after Isaac Newton, the great mathematician and physicist. That is actually the next remark, and this remark appears in the text before the proof. This is your remark 10.1.8. And the remark, of course, is just simply that this approximation is named after Isaac Newton. So there is no point writing it again. And the proof, of course, we won't do it here. In fact, the proof is one of the exercises at the end of this section. And you know very well that we will do these things in community posts. So we will skip the proof now and see what lies ahead. In fact, we will see the proof in exercise 2. But then there is another remark, which in fact is about this approximating nature of this result. So we have another remark. This is going to be 10.1.9. And this remark is simply this: we can phrase this above proposition in a more informal way. Proposition 10.1.7 in a more informal way or manner as follows. If f is differentiable at x naught, without going of course into the details of everything, that x naught is the limit point and so on. So okay, so if the main thing is this: if f is differentiable at x naught, then f of x is approximately equal to this expression. Near x naught. Okay, let's also add that, provided x is sufficiently close to x naught. Maybe this language is not okay, because sufficiently means sufficient for what? Here we are not setting any bound like epsilon on the difference between fx and this expression. So maybe I should drop sufficiently and simply write vaguely that x is close to x naught. That is this remark. And in fact, you can appreciate this approximation even more if you think about the whole situation geometrically, which is not what the author has done, but let's just see, okay, what this entire thing means geometrically. You see, roughly a function being differentiable at a point means what for the graph of the function at that point and around that point? The graph is smooth, that it does not have any sharp bend at that point. The graph is how you normally know graphs. Okay. For example, say this is the graph. We are not, of course, showing the entire graph of our function f, but only maybe a small portion of the graph. which is near x naught. Okay, and if one draws a tangent to the curve at that point x naught, our function of course has the graph which is a curve like this. However, the tangent is a straight line. Now, if you think about this equation plus L times x minus x naught. This is a linear equation in x and y. Now, if you rearrange the terms, the equation takes this form. Right? And from coordinate geometry, you know what this line is. It is that line which passes through the point x naught comma f of x naught and which has slope L, because in this form, this is the point slope form of the equation of this line. Okay, it passes through this point and has slope L. And we also know from the geometric analysis of derivatives, I mean from our school courses, that this L is actually nothing but the slope of the tangent at that point. Okay, so that means this equation we are looking at is actually the equation of the tangent at the point x naught. Well, of course, this itself is not x naught, but it's the point x naught comma f of x naught. But in what sense are we having approximation? Numerically, of course, this value is going to be approximately equal to this value. However, provided we are choosing our x close to x naught. Now, if you think about this whole thing geometrically, you see this is the linear approximation because it's a straight line. Our original function is in most of the cases not going to be linear. Okay, so the graph around x naught is going to curve. However, if you just think about it, thus closer you are to x naught, within that region, the curve is almost like the straight line. And the smaller your region is around x naught, the more indistinguishable these two things are going to be, the curve and the straight line. And if you are sufficiently small, okay, if your region around x naught or neighborhood of x naught is sufficiently small, then the curve will be almost like the straight line. So in that sense also we have an approximation. Okay, so that is the real meaning of Newton's approximation. This, however, is only possible provided there is a tangent, and that is equivalent to the function being differentiable at that point. Differentiability and existence of tangents are equivalent. Alright, now let's move on. Here the author has not discussed these things primarily because we are not really interested in geometry that much. We are interested in the analysis of these things. Okay, now we have already come across this. We have already seen that the function from R into R given by this, that is our well-known absolute value function, is not differentiable at x equal to 0, but is nevertheless continuous there. Continuity of this function we already know. Okay, we all saw the continuity of this function even before we started differentiation formally. But we have also seen that the function is not differentiable at x equal to 0. However, if a function is differentiable at a point, then it has to be continuous at that point. So this next result is about that. It is going to be proposition 10.1.10. Differentiability implies continuity. Which also means that if a function is not continuous at some point in its domain, then it cannot be differentiable at that point. And the statement, of course, is just that. It's just that. It starts off just like how we started Newton's approximation. Let x be a subset of R, x not be an element in X, let this be also a limit point of X, and let f be a real valued function with X as its domain. Then, if f is differentiable at x naught on X, then f is also continuous at x naught. We need not even mention what the derivative of f is at that point x naught. Just the fact that it is differentiable with some derivative, of course, that fact alone implies that f is continuous at x naught. And its proof also is one of the exercises. The third one. After this we have so far defined differentiability of a function at a point, but now we are going to see differentiability on a domain, okay, on a set. So this is the next definition, and it's 11, item number 11. let X be a subset of R and F be a real valued function on X. If F is differentiable at each element x naught in X on X, then we say that F is differentiable on X. That means if F is differentiable at every point on its domain, then it's called or it's said to be differentiable on that domain. Okay. And from our proposition 10.1.10 and this above definition, that means differentiability implies continuity, that proposition and this definition, we immediately have this next corollary. Let X be a subset of R and F from X into R be a function. If F is, let me write on that side. If F is differentiable on X, then F is also continuous on X. And this corollary, of course, needs no proof. It is just an observation. We need proofs of only the other results that we have seen before this. In particular, we need the proof that differentiability implies continuity. That alone automatically implies this. And let us just end here itself. After this, we have algebra of derivatives with which you are all very familiar. How to differentiate the sum of two differentiable functions. Difference, product. In fact, we have a product rule for differentiation and the quotient of two functions. For that also, we in fact are all we are well familiar with these formulas. We have been using these things in calculus. We have done that many times. We are going to see that result, and we are also going to see that composition of differentiable functions is itself a differentiable function. And from that we are going to see a formula which is basically nothing but the chain rule in a single variable calculus. So with these things that we will see in the next upload, this section is going to be over, and then the exercises will start. So that's just it for tonight. See you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.